Hello everyone and welcome. Today we're going to crack open the toolbox of master programmers. We're talking about the secret weapons, the real master keys that let you solve some of the toughest puzzles in the world of tech.
So just imagine for a moment, you have a problem with millions, maybe even billions of possibilities. How do you even begin to tackle that? Say, finding the best route that connects 1,000 cities, or comparing huge strings of genetic code. You can't just try every single option, can you? That would take forever. You need a more clever, a more elegant way. So let's dive into our first secret weapon. And our first one is a very powerful idea called dynamic programming. Now, don't let that fancy name scare you. At its heart, it's actually a very simple, very human idea. If you've already done some work, why on earth would you do it all over again? It's all about being smart, being efficient, and not wasting your effort.
And this is the core of it, really. You take a massive, scary problem and you just slice it into smaller, manageable pieces. You solve each of these tiny pieces just one time. And here, this is the magic part. You write down the answer. You store it, you save it for later. In programming, we have a fancy name for this: memoization. It's just a way of saying, let's remember our work so we can make our future life easier.
This slide just shows the difference so perfectly. You see, the normal, naive way is like someone who calculates what 2 plus 3 is every single time they see it. But the dynamic programming approach? That is the clever student who writes down 2 plus 3 equals 5 on a piece of paper and just looks it up later. And for a computer, this isn't just about saving a few seconds. No. This is the difference between solving a problem in a minute and it taking a million years. It's that big of a deal.
Okay, so theory is one thing, but, seeing is believing, isn't it? Let's jump into a classic example and actually watch this remembering technique work its magic in some real code. So the problem we'll tackle is called the longest common subsequence. The goal is simple: find the longest string of letters that shows up in two different words, in the same order. So, for example, what is the longest thing that sequence and subsequence have in common? This kind of problem is just a perfect candidate for dynamic programming.
And here is the code. Look, this function, LCS helper, it breaks the problem down again and again. But look here, look closely at this line, Cij equals Q. This is the heart of dynamic programming. All it's saying is, hey, for these two smaller pieces of the words, the answer is Q. We are storing that answer, Q, in our table, C. It's like we are telling the program, listen, remember this. If you ever need this answer again, don't you dare recalculate it, just look it up. It's so simple, but so incredibly powerful.
And this table you see? This is the program's memory. You can think of it like its own little notebook. As the code runs, it starts filling in this grid with all the answers to the tiny subproblems. So by the time it gets to the end, it has built up the final, complete answer from all these small stored results. And the best part? It never, ever had to do the same work twice. Brilliant, isn't it? All right, let's completely switch gears now and look at our second secret weapon. Now, what if the goal is not to find the best solution, but just to find any solution that works? Well, this requires a totally different mindset. Not one of planning, but one of exploration. So welcome to the world of backtracking.
The best way to think about this is to imagine you are lost in a very big maze. What is your strategy? Well, you try one path, right? You keep going. And if you hit a dead end, a wall, you don't just give up. You simply go back, you backtrack to the last place you made a choice, and you try a different path. This is exactly how a backtracking algorithm thinks. It is a tireless explorer. It just tries and only retreats so it can try a new way.
Let's see this little explorer in action with another classic problem: the rat in a maze. It's very simple. We have a grid, a start point, an end point, and some walls that are blocked. Our job is to find a path for our little rat to get from the beginning to the end.
Now, this code, this is our rat's brain. It explores. It says, okay, let's try moving down. Okay, now let's try moving right. But what if it gets stuck? What if it hits a wall? Now look at this line here. Sol xj yj equals 0. This is the backtrack moment. The code basically erases its last step. It says, oops, wrong turn, and it goes back to the previous spot to try a different direction. It's so simple. When it hits a dead end, it just backtracks. And there you have it. This is the result. By trying every possible path and very smartly backtracking from every single dead end, our algorithm eventually finds a way through.
It has successfully explored the entire maze and found a solution.
So, what we have seen are two very different but equally powerful ways of thinking. Both of them are designed to solve very complex problems, but they go about it in completely opposite ways, don't they? Let's just put them side by side and summarize what makes them unique.
This table sums it up perfectly. Dynamic programming is like the careful, meticulous planner. It builds the perfect, optimal solution from the ground up, piece by piece. Backtracking, on the other hand, is the adventurous explorer. It just dives in, fearlessly trying one whole path and then another and another. So you see, the planner finds you the best way. The explorer simply finds you a way that works.
So please remember, these are not just algorithms, they are mindsets. They are different ways to approach a problem. And the sign of a truly great programmer is knowing when you need to be the planner and when you need to be the explorer. So I will leave you with that question to think about. Which one will you be? Thank you so much for joining me today.